Okay, guys, so let's get into equilibrium. So equilibrium, let's go over definitions real quick, and then we will get into actual problems. Okay, so equilibrium is, you guys might be able to tell just based on the vocabulary that it's a state of balance. It's where things are equal to each other, right? Now, chemical equilibrium basically means that when you got a reaction, it can go forward and reverse, right? We talked about the rate of a reaction. Equilibrium is where a reaction, the forward rate and the reverse rate is equal to one another. Okay, so if you want to make it very simple, basically the forward rate is equal to the reverse rate. That is what chemical equilibrium is. Okay, so when you got a reaction, it's going forward and backwards at the same rate. That's equilibrium. Yes.
So would that be notated by those arrows that were?
Yeah. So yeah, you guys might have seen those arrows. It's where you have a reaction and it looks like this. Okay, there's a forward rate, a reverse rate, and it's equal to one another. So it's going back and forth at the same rate. Yes.
Is that always true, or is that only?
Always true. That's the definition of equilibrium. Yeah. Now there's some nuance that we need to talk about, but so make sure you guys keep that in mind. Okay. Okay. Basically, what it means is that the concentration of the reactants and products, they don't change over time. Okay. So we got a quick example here. And in this reaction, you have N2O4, which is a colorless gas. So it starts like this. And then what happens is it starts to produce NO2, which is a brown gas. Okay. So it starts like this. It's colorless. Then it starts slowly turning brown. And then it gets to a point where it gets to this, I guess, kind of diarrhea looking color. And it just stays there. Okay. The forward and reverse rates are the same. And the color stops changing. Okay. All right, now the key thing to note is that equilibrium is about rates. It doesn't mean you have the same amount of reactants and products. It's the rate of the reaction, okay? So let's take a look at this. Okay, so this is just a bunch of information about it. You guys can read through this in your reading, which everybody does on time, right?
No.
Right? Of course, yeah, already did this, right? Yeah. Okay, you did? Good for you, scholar. Okay, not bad. I don't think I even read it twice. Okay, so anyway, so the key thing is that it is about the rate of the reaction. Okay, it's when the rate forward and reverse rates are the same. It doesn't mean that it's the same concentration. Okay, so equilibrium is not this. It's not about the concentration of the reactants and the products. Okay, so it's not this. It's about the rate. Okay. And basically what we do is we want to find something called an equilibrium constant. And it's just the ratio between the products and the reactants. You guys this might look familiar from previous units where we find a constant. But when we have a reaction like this, we just put the concentration of the product divided by the reactant, and that's equal to the forward rate and the reverse. Okay, yeah.
So there's no single constant for equilibrium that differs between equilibrium.
No, there's gonna be a equilibrium constant, and this is how we calculate it. Yeah. There's gonna be a number. You'll get like 0.9. Or like, yeah. Yeah. Okay, but the key thing to note right now, I know this is a lot of words and a lot of text, but the key thing to note is equilibrium is when the reverse and the forward rate are equal to each other. It's not about the amount of products and reactants. Okay. Any questions so far about the definitions? Yes.
Sorry. So
no, you're good.
Does the equilibrium constant change between different reactions?
Yeah, different reactions will have a different. Yeah. It's almost like the kinetic unit. Yeah. Okay, so just a couple graphs to kind of demonstrate that. Okay. So this is talking about the concentration. Okay, so this is going to be the concentration over time. If you guys notice, NO2, you start with no NO2, and you start with, let's say, I don't know, 1 molarity of N2O4. Okay, as time goes on, you lose N2O4, and as you lose it, it produces NO2. And it gets to a point where we reach equilibrium. That's where the concentration stops changing. Okay, so the concentration stops changing. Okay, that's what equilibrium is. It's where you get to a point where the reactants and the products, they have a set concentration and the concentration won't change. Okay. But if we compare it with the rate, it's where you start with different rates and they get to the point where the rates are equal. Okay. So at equilibrium, the rates are equal, but the concentrations don't necessarily have to be equal. And a lot of times they won't be equal to one another. Okay. That's the basic gist of equilibrium. Okay. Any questions about that, or does that make sense? Yes.
So equilibrium is kind of just, that kind of just be when the reaction kind of stops happening, or would it just be when the reaction?
The reaction is still taking place, but the forward reaction is happening at the same rate as the reverse. So it's basically as this happens, an equal amount happens this way. Yeah. Okay. All right. So now we can do math with it. So we're going to be calculating the equilibrium constant. Okay. So we're going to be looking at this sample equation. Okay. And then let's write the equilibrium constant for it. Okay. So the equilibrium constant is very simple to write. It's very similar to the constants that we wrote before. It's basically products divided by reactants. You guys might be familiar with that already. Okay. So let's write the equilibrium constant for this reaction right here. Okay. Okay, so we're going to use this kind of as our framework. Now we're going to put the products on the top. Okay, so the equilibrium constant for this reaction is going to be equal to the concentration of our product, which is NH3. Okay, and unlike the kinetics unit where sometimes it could be a different one from the coefficient, the exponent's always going to be what the coefficient is. So the coefficient is 2, so we put a 2 up there, divided by the concentration of the reactants. Okay, so that's how you can calculate the equilibrium constant. Okay, it's just products divided by reactants. Okay, and this basically tells us the ratio at equilibrium between the products and the reactants. Okay. So I see the life draining from your eyes already. You guys are so happy like 10 minutes ago. It's Monday and the first day back. Are you?
What? So you said this was it? So your least favorite unit was
Kinetics. Or it's electro. It's electrochem. And then it's kinetics. I like equilibrium. It's the very last one. What's up? Yeah. Yeah. This is the equilibrium constant of this reaction.
There's no numbers in here, just this formula.
Mm-hmm. Yeah. We'll have numbers in a sec though. Don't worry.
I know.
Yeah. So this basically tells us how much product we have relative to the amount of reactants once we get to equilibrium. Okay. Alrighty. So with that being said, we just did 12.1. It was that. Okay. Okay. So the equilibrium constant is going to depend on your balanced chemical equation. Okay. Because obviously the exponents are dependent on the coefficients, right? And so the coefficient is going to tell us what the exponents are going to be. Okay, so I'm going to give you guys some time. I'll give you guys 2 minutes. I want you guys to write the equilibrium constant, the expression Kc, what we just did for these two reactions. Okay, just to give you guys a little bit of practice. Take about 2 minutes. You can work with the person next to you. I want you guys to write the equilibrium expression for these two reactions. All right, take about 2 minutes to do that. Okay, so hopefully this wasn't too bad. For part A, Kc is equal to the concentration of O2 cubed divided by the concentration of ozone squared. Okay. And then for this one right here, it'll be your product. Very long. Okay. And then its coefficient is 1, so we just leave it, divided by the concentration of silver ion, and then ammonia on the bottom squared. Okay, everybody got that? Okay, so pretty simple. This is just the baseline of how we write the equilibrium expression. Okay. And it won't get much harder than this. Psych. Psych.
Yeah,
All right.
we-
Of course it won't, will.
It's 37 pages.
Oh, is it?
Yes.
Dang, dude. I put in way too much work into this. I must care a lot about you guys. Yeah, I wrote all of them.
Like to use them.
Yep, I did. Yeah, I was thinking of you guys when I wrote it 3 years ago.
If I ever become a chemistry teacher, I'll copy all your.
You know, I'm gonna sue you for copyright.
Videos, just watch the video.
That's literally what our teacher did.
I
She
should
would
do
put on
that.
some of your videos.
Okay, so equilibrium concentration. We've been talking about in terms of concentration, so molarity, right? Now, another way that they might talk about equilibrium on the AP test is in terms of pressure. So if we are working with the equation where all the compounds are gases, since we operate under the assumption that all gases are ideal gases, we can talk about them in terms of partial pressure, okay? So same thing, we can write a partial pressure equilibrium expression, and it's going to be the same thing, but instead of concentration, we do it with pressure, so atmospheres, torr, etc. So it's the same process, okay? And then we can also calculate it using the equilibrium constant with this equation right here, okay? It's a lot of words. So with that being said, I'm going to give you guys maybe about 2 minutes to try this one out right here, 12.3. Okay, so we got a reaction. The Kc is 9.6. Temperature is 300 degrees Celsius. I want you guys to calculate Kp. Okay, and then delta N is the one that you guys might not be familiar with. It just means the moles of the product minus the moles of the reactant. So we haven't really explicitly gone over that yet, but see if you guys can figure this out. I want to kind of put you guys in interesting scenarios because you won't see every type of problem that's on the AP test. Try to figure that out. I'll give you guys about 2 minutes and then we'll go over it together. The word. Okay, so 12.3, we are solving for Kp. So we're just going to use this equation right here. Okay, so Kp is equal to the Kc, which is 9.6. So we're going to do 9.6. And then what we're going to do is we're going to multiply it with the ideal constant, or ideal gas constant, 0.0821. Okay, we got to get the temperature, but since it was given to us in Celsius, we have to convert it into Kelvin. It's going to be 573. Okay, and then what we have to do is we need to raise it to the power of the change in moles of the gas. Now, we got to look at the equation in order to do that. So if you guys take a look at the reactant, how many moles of gas are on the reactant side? How many moles of gas are on the reactant side? Yeah, 4. Okay, there's 2 different types of gases, but we got 1 mole of nitrogen and 3 moles of hydrogen, right? And so we start with 4 moles of gas. And then on the product side, how many do we have? 2. So we go from 4 to 2. So the change is going to be -2. Yes.
So, are we gonna do equation where it's not all gases?
Yeah, so where it's not all gases, this doesn't apply at all. This is only for if the entire system is based on gases. Yeah, good question. Okay. All right, so if you calculate that out, you should get 4.34 times 10 to the -3. Or you can get 0.00434. Something like that. Yes. No, not necessarily. If you want to put it in this form, you can. No. I mean, if it was like, if the answer was like 0.000000000, then they probably would. But something like that's close enough. 2 to 3, I'd say. Yeah.
So we need to do
No, not for this, because it's a ratio. Yeah. Good questions, guys. All right. Any other questions? Not too bad. Yeah, so just keep in mind though, I guess the trickiest part here would be the delta N. It could be a positive or negative number depending on how the reaction goes. Okay. All righty. Let's move on. We're going to skip 12.4. And now we're going to talk about what these equilibrium constants mean. Okay. Okay, so we got a sample equation right here, and we have its equilibrium constant, and let's say the equilibrium constant is this value right here. Okay, so if the equilibrium constant is very large, what that means is that the numerator, the number on the top, is going to be a lot bigger than the denominator, right? And so this kind of gives us a way to evaluate what the reaction will look like just based on its equilibrium constant. Okay, so if the K value is very, very large, that means equilibrium lies to the right, which means that once you hit equilibrium, you will have a lot more product than you will have reactants. Okay, so this is a good example. It's basically like 4.5 billion. So if the K value is 4.5 billion, you have 4.5 billion moles of product for every 1 mole of reactant. And so you have a lot more product. So that we express that by saying equilibrium lies to the right, so the right side of the equation. Okay, but if you have a very small K value, and that's going to be if you have like a very small decimal, so like 0.0000 whatever, like 3, that means that you're mostly going to have reactants. So equilibrium lies to the left. So just want to get you guys familiar with those terms. Yeah.
So the equilibrium, that was like the previous equation, was that 9.6?
The one that we 9.6.
So that would be smaller.
It would be it's a what is it? If it's over 1, it lies to the right. Yeah, because 1 is where you have an equal amount of products and reactants. If it's greater than 1, then it's going to lie to the right, more products. And if it lies to the left, it's going to be a decimal. Yeah, good question. Okay. So yeah, 1 is kind of that middle. 1 is where you have the same value, and you're rarely if ever going to have an equilibrium constant of 1. Okay. Yes. You'll have a way to find the difference every single time. Yeah. They'll either give you the equilibrium constant or you'll be able to calculate it. Okay, so what I want to do now is I want you guys to, as soon as you're done writing what you're writing, I want you to drop your pencils. Everybody drop your pencils and hands up. Okay. No, you don't have to put your hands up. Okay, but let's take a look at this system right here, okay? So we're going to do part A together, and I want you guys to take a look at the first box right here, okay? So if the volume of, let's say all the containers have the same volume, 1 liter, and each single one of these spheres is 0.1 moles, okay? We're going to do part A. I want you guys to rank these in order of increasing equilibrium constant, okay? So which one is going to have the highest KC? So I want you guys to take a look at it. You can discuss it with the person next to you. Don't calculate it. Just by looking at it, I want you guys to talk about with the person next to you, which one has the highest equilibrium constant and which one has the lowest. Take about a minute to do that. Rank them in your head, and then we'll go over it together, okay? All right, guys, so let's go through it, okay? So hopefully you have your answer locked into your brain. Okay, so the pattern that we need to follow is that if you have more products, okay, is the K value going to be bigger or smaller? Yeah, you're going to have a bigger K. Okay, so the more products that you have, the bigger the K, and vice versa as well, right? The less products you have, more reactants you have, the smaller the K value. So if you guys take a look at these, which one of these boxes has the most products relative to the reactants? Yeah, the third one, because the red one is the product, right? The products are on the right side. And so this one has basically all red spheres and only 2 blue ones. And so this one is going to be the highest K value, okay? Now, we got these 2 to look at. Which one do you think is going to have the lowest K value between the 2? Yeah, 2, because there's only 1 product, right? Relative to all these right here. So your order right here is going to be 2 is the smallest, and then it's going to be 1, and then it's going to be 3. Okay, so that's going to be your rank. Okay. Basically, more products means higher K value. Okay. All right. Any questions? Pretty easy. Okay, now I'm going to let you guys use your pencils again. I'm sure some of you guys are already using them, but whatever. I want you guys to take a look at just this system, and I want you guys to now calculate the exact K value for just the first system. I'll give you guys the K values for the second and third one in a bit, but I want you guys to use the information right here, and I want you to calculate the K value for the first system right here, the red and the blue one right here, okay? So I'll give you guys a minute to try that out, and then we'll go over that and then compare it and see if our ranking right here is accurate. Okay, so if we take a look at this first system, all we got to do is compare the product concentration and the reactant concentration. So all we got to do is basically count up these spheres. So 1, 2, 3, 4, 5, 6 is going to be the value for our product. So each one is 0.1 mole. So it's going to be 0.6 on the top divided by 1, 2, 3, 4. And that's going to be 0.4 on the bottom. So we'll get a value of 1.5. Okay. That's going to be our K value for this system right here. Okay. And then if we calculate the other ones, which I didn't have you guys do, you'll get 0.11 and 4. And then you guys will notice that this prediction that we made without calculating is accurate. Okay. That's pretty much it. All you're doing for the K value is looking at the ratio between products and reactants. The more products there are, the higher the K value. Okay. Easy peasy. Yeah, relative to the reactants. Yeah. Okay, let's move on. Oh, you guys can try 12.6. So I'll give you guys about 2 minutes to try 12.6. This one is kind of an FRQ style problem, I guess. I want you guys to answer the question, but also explain it. Okay. So 12.6 for the reaction, you got KP at a certain temperature, and you got a KP when it's at a different temperature. I want you guys to tell me if the formation of the product is favored at a higher or lower. Oh, it's dying. Oh, okay. Yes, take about 2 minutes. Try that. Try to answer it and explain it, and then we'll go over it together. All right. Okay, so if we take a look at this reaction right here, it tells us that the KP is 794 at 298 Kelvin, and then it's 55 at 700 Kelvin. Okay, now we're looking at the formation of the product. Okay, so is the product going to be favored at higher or lower temperature? Anyone want to take a shot at it? Yeah, run. Why do you say lower? You're stealing answers. Okay, Brendan says lower, which is correct. Sure, you got that all by yourself, right? Okay, so why is it favored at lower temperature? Yeah, exactly. Easiest way to say it, KP is higher at lower temperature. That's basically it. And that basically tells us that you got more products relative to reactants at 298 Kelvin than 700 Kelvin, something like that. Okay. So depending on temperature, your KP value can change. And in this situation, the lower the temperature, the more product you will have. Okay. That's it. Great job, Brendan. Of course. Josie, you might want to ask him for some help, okay? That evil laugh. Alrighty. You guys ready to move on? Alrighty, let's move on. All right, so there's a lot of writing here. I'm not gonna force you to read it. Just the easiest way that I can describe this part right here is that the forward and the reverse reaction, the K value is the reciprocal of one another. So it's just the inverse. So for example, if we're going in the forward reaction right here, okay, the K value, and you guys don't need to write this down, is going to be products over the reactants. Okay, this is what we've been looking at, right? Okay, but if we look at the reverse reaction, okay, the K value of the reverse reaction is just going to be the inverse of that, right? It's because this will be the new product, if we're going this way, divided by the reactant, which is on this side. Does that make sense? So depending on the direction that you're going, the K value is going to change. and the K value is just going to be the reciprocal or the inverse of the two. Okay, so just keep that in mind. You guys good with that? All right, just making sure. Okay, so it tells us here that the K value is bless you, 0.212. So this value right here is 0.212. That means for the reverse reaction or the opposite reaction, it's just going to be the inverse. So 1 divided by 0.212, okay, which happens to be 4.72. That's probably experimentally derived. Yeah. Okay. So basically, if you have one of the K values, you can find the K value of the reverse reaction. Just do 1 divided by that. Okay. Just flip it. Okay. So keep that in mind because we're gonna be adding some more things to it. Oh, I guess we're. Oh, I'm sorry.
Sorry.
No, you're good. No, you're good. I'll leave it up there. I want you guys to marvel at my amazing handwriting. Thank you, but I know it's not. I got in trouble in first grade for my penmanship. No. Yeah.
Wow.
Mrs. Stewart. She was a nice lady, but she said I had bad handwriting.
You got in trouble.
Yeah. Because she couldn't read my work. And then she told me to fix it. I didn't listen to her. I ain't gonna listen to Mrs. Stewart. Huh?
Gosh, that sounds good.
I feel like you have some pent up you have
I-
resentment. Yeah.
I don't. I really don't. She was a very nice lady. She was. She was really sweet.
Sort of all the bad aspects of every teacher you've ever had.
Basically, and I become all of them. How do I be exactly? It was in first grade when I knew that I want to be a teacher and give people crap for their handwriting. Okay, you guys good with this?
Now you have all the power.
I do have all the power. Mad power trip. Okay, so let's do 12.7 really quickly. I'll give you guys a minute to try this. You guys got this reaction and the K value. I want you guys to calculate the K value of the reverse reaction. Okay, basically what we just went over. Just want you guys to practice doing it. Plug it into a calculator. We'll go over it in 1 minute. Okay, so try 12.7. Okay, so the K value of this reaction is 1 times 10 to the negative 30. Now, if we're taking a look at the reverse reaction, all we need to do is find the inverse of that. And if you plug it into your calculator, you're just going to get 1 times 10 to the 30. That's it. Okay, so if you want to find, again, the K value of the reverse reaction, you just invert your equilibrium constant.
It's just 1 over.
Yeah, 1 divided by 1 times 10 to the negative 30.
So it's just positive action.
Yeah,
Wow.
yeah. Making it easy for you guys. Of course, my pleasure. Okay, so we're gonna add some other stuff to analyzing these equilibrium constants. Now, the equilibrium constant is going to depend on the stoichiometry of the reaction. Now, if you guys remember, we use the coefficients to write the equilibrium constants, right? And so depending on the coefficient, that's going to change the value of the equilibrium constant. Okay, so for example, if we multiply this equation right here by 2, okay, that's going to end up squaring the equilibrium constant because we have to basically square the coefficients. The coefficients have an exponential relationship to the concentration and the K value. So if you double it, right? If you double this, it's going to become squared. If you double that, it's going to become to the power 4. So that's going to end up squaring our equilibrium constant. Okay. So the stoichiometry, the coefficients have an exponential relationship with the K value. Okay. Okay, so let's take a look at 12.8 now. So for 12.8, this isn't giving us any numbers, but we do need to analyze this and talk about magnitude. So I'll have you guys try this. Okay. How does the magnitude of the KP for this reaction right here change if it's written like this? Okay, so what you need to find is the relationship between these two and how that's going to change the magnitude of the KP value. So you don't have exact numbers, but you're going to have to be able to explain how the magnitude changes. Take about a minute to do that. We'll go over it. And then, yeah, we'll move on to where we kind of combine all this together. I think that'll be the last thing we do today. Okay, so if we take a look at the first equation right here, the Kp value is going to be equal to the partial pressure of your products, so H2 and I2, okay, divided by the partial pressure of HI, I squared, okay? So far, so good on that? Okay, this might not have been in your answer, and that's fine. This is just part of the explanation. Okay, so this is the first reaction right here. Okay, so I'll put like a black smiley face here, and I'll do a red one right here. Okay, so for the red one, it's going to be the same thing. The Kp value is going to be the partial pressure of H2, but this one we have to the power 3. And then the partial pressure of I2, this one also to the power of 3, divided by the partial pressure of HI, this time to the power of 6. Okay, now if you take a look at the relationship between the two reactions, how did this reaction change? What did we do to the coefficients? Yeah, we tripled it, right? So the coefficients, okay, we tripled it, okay? But when we triple the coefficients, what happens to the Kp value? Yeah, we cube it. Good word, guys, cube. Okay, we cubed it, or you can say it's raised to the power of 3. Okay, so yeah, just an exponential relationship. If it was multiplied by 2, we would square it. If we multiply by 4, we would whatever that is. That's it. Yeah.
So you just say that you.
Yeah, Kp cubes when the reaction is multiplied by 3.
So that's what I put, but like, is it ever gonna be different? Like, does it matter how many products or reactions there are?
If you multiply the whole reaction by a certain number, then it's gonna have it's gonna correlate exactly. Yeah, because they all change the same amount, or relatively the same amount. Yeah, good question. Alrighty, guys. So we're gonna take this and that inverting thing, and we're gonna put it together. And what we're gonna look at now is what happens when we have a reaction that takes place over multiple steps. You guys remember Hess's law? We have to organize the reaction, cancel them out, add it up together. I know everybody loves that, right? Oh, okay. All right. Well, good. That's the point. All right. Now, the last thing we're going to add on to that is that the net sum of the equations, you can basically combine equations together in order to find a combined equilibrium constant, okay? So I think the best way to do this is to just do a problem. This is kind of my summary of it, but it's basically what we did before with thermo and things like that, okay? So let's jump right into 12.9. We'll try it together, and then I'll have you guys try 12.10. And I think that should, oh, we might have more time. Okay. 2:01. Alrighty, so let's do 12.9 together. If you guys think you can do it without me, then you can just kind of ignore me for a little bit and try it out. But let's do it. Let's go over step by step just in case. Okay. So what we want to do is we want to combine these two equations in order to get this final equation right here. Now we're gonna have to manipulate it a little bit. We can't just combine it together. Okay, so let's take a look at this final equation. Now it looks like we have HF on the reactant side. So we're gonna want to make sure that we have HF on the reactant side for the reaction we're working with. So if we look at HF, we got HF in the first equation right here, but we only have one. So what do we have to do to this equation in order to fit this equation, the final one? Yeah, you got to double it. Good. You're going to double the first equation. That's going to give us 2HF. And that's going to produce H plus and F minus. Oh, sorry, 2. Okay. Now, if we double an equation, what happens to the K value? Not doubled, it gets squared. Yeah. Keep that in mind, guys. Okay, it's different from thermo. In thermo, we multiplied it by 2. But when it comes to equilibrium, we have to change the exponent, which is we're gonna square it. Yes. Yeah, it has to. It's because of the rates. Yeah. Okay, cool. We did that. All right, now we have HF on the left side, so we got this one taken care of. Now let's take a look at C2O4. Okay, so if we take a look at C2O4 2 minus, It's on the opposite side right here, right? So what we have to do is we need to flip the equation, exactly. So if we flip the equation, we're gonna have 2H plus on the reactant side. We're also going to have C2O42 minus on the reactant side. And then we're going to have H2C2O4 on the product side. Okay, now if we flip it, what do we need to do to the K value? Not negative. Yeah, inverse or reciprocal. Yeah, negative is for thermo. Yeah. So if you guys are thinking of thermo, then that's correct. But when it comes to equilibrium and rates, we need to find the inverse. Okay. So far, so good? Okay. Now let's just make sure that we got everything correct. Now we need to get rid of all the intermediates. So we're going to combine this equation. Now, what can we cancel out in this reaction right here? Yeah, H plus, because we have it on the product, but it's used in order to fuel this reaction right here. So if we combine this reaction together, that's not a very straight line. And neither is that. That's a little better. Okay, so we're going to have 2HF on the reactant side. Okay, we're also going to have our C2O42 minus on the reactant side. And then we're going to bring down the products. And then we're going to have 2F minus, the grade you're going to get in this class. And then we're going to bring down this right here. Okay. All right, now let's just make sure everything lines up. We got 2HF, C2O42 minus, 2F minus, H2C2O4. So we're good to go. The reaction, we did all the manipulations that we need. Now all we need to do is find the sum of the equilibrium constant. So I will give you guys a minute to try that out, see how good you guys are with your calculators. See if you guys can figure out what the final equilibrium constant for this final equation. So I'll give you a minute and then we'll go over it, make sure we all got the same number. Okay, guys, so hopefully you guys got your final value, and your final K value for this equation is going to be 0.122, something around there. Did I get it wrong again? Okay, give me a... We do need to add them afterwards. Okay, give me a sec. I might be wrong. Okay. I know. Who am I? Okay, so the red one. We should get 4.624 times 10 to the negative 7. Yes?
Yes.
Okay.
Yes.
Okay. Just making sure. Okay, and then for the blue one. Oh, wait, hold up. I told you guys the wrong info. My bad. Fake news. It's not adding. It's the product. Sorry, guys. I was thinking of thermo. Yeah, it's the product. I'm sorry. Okay, guys, it's been a long break for me. It's the product. Yes. Yes, of course. Okay, sorry. Yeah, you have to multiply the two values. My bad. Not add them. I know I said add. I was thinking of thermo as well. I apologize. Will you guys forgive me? That's fine. Yes.
So if we had like an FX question, could we like explain this and call it Hess's law, or is it different?
It's not Hess's law. Yeah, don't call it a Hess's law. You probably won't have to explain this either.
But like in theory, what would you call it?
You can just say that you are finding the you're finding the equilibrium from multi-step reaction.
Oh, now I got it.
I apologize, everybody. I think you should. Because I'm basically ruining your future like this. Like, you're gonna get this wrong because I've messed you up. Exactly. And then you're not gonna go to college. And then you're not gonna get a job. And then you're gonna die of sickness and hunger. That's basically all my fault. Like my poster, yeah.
How did you?
What's up?
Oh wait,
Yeah. Yeah, sorry about that, guys. Basically, you just need to calculate these and then multiply them together. I apologize. I forgot. Okay, yeah. That's fine, yeah. It's probably the way that we rounded on the calculator. As long as you have 1.1 something, you should be good. 1.7? Okay, sorry, I thought you meant 0.17. No, that's way off.
No, yeah.
Yeah, you might want to double check. Yes.
How did 6.8
You square it.
That's the donor.
6.8 times 10 to the negative 4 times 6.8 times 10 to the negative.
No,
Uh-huh.
it's,
Yeah. But the inverse though, 1 divided by, yeah. Basically, you can divide it by 3.8 times 10 to the negative 6. Yeah. Yeah, so for this one right here, if you don't have the square function, you're gonna have to do this times this. And that's gonna give you 4.6 times 10 to the negative 7. So far, so good? Okay. And then if you have to multiply it with this. And so what you're basically doing is times 1 divided by 3.8 times 10 to the negative 6. Now, an easy way to do that is just to do 4.6 times 10 to the negative 7 divided by 3.8 times 10 to the negative 6. And that should give you an answer of about 0.122. Yes.
Why didn't you just try to make it 3.8?
Because remember, we flip the reaction. If we flip it, we have to invert the K value. Because it started with H2C2O4 on the left side. Oh, like the previous example, that was because the number in the front was 1. It only works when it's 1. Yeah, you still need to calculate it out. Brendan, does that answer your question?
Yeah.
Okay. Yeah. Sorry, I know I confused you guys, but pretty much that. Okay, let's see if you guys can try one on your own. I know that there was a lot of, we're working out the kinks. It's the first problem with this. So I'm going to have you guys try 12.10 on your own. Okay.
After that, we're done.
Maybe. I think so. It looks like the time is going to be like that. Okay, so I'll organize it so it's a little bit easier for you guys to look at and to read. Okay, but these are your 2 reactions. And I want you guys to determine the K value for this reaction right here. Okay. So I'll give you guys about 6 minutes to try that out. I know it's a longer problem. Let's see if you guys can get the KP value for this reaction right here. Okay. So this one right here, basically same stuff we're doing. I know that it's KP, but it's basically the same. We can use the same processes for KC. And we want to make this reaction. So I'll go through it a little bit quickly. I'll make this one the red one, and I'll make this one the blue one. Okay, so let's start. So first thing we're going to do is we're going to invert this one right here. We're going to switch up the equation, and you should get this right here. Okay, that's going to make the KP value, yeah, 1 over whatever the KC value for that is. Okay. Okay. So far, so good? Okay. All right. Next thing we're going to do is we are going to have to triple the first equation, the red one. So let's triple it. We're going to triple this right here. We're going to have to triple I2. And then that's going to make this 6 HI. And that's going to make our KP value. Yes, exactly. Took the words right out of my mouth. Okay. All right. Yes. What was that?
It's 54 to
Am I?
They like line up weird.
Oh, my bad. I apologize, guys.
Yeah, that happened in me too.
I lined it up wrong. So many mistakes today.
It's a Monday, Mr.
I know.
And the first
I
day
don't.
back from break.
I don't. You guys are so gracious with me. I would never be this gracious with you. Okay, and then yeah, 1.04 times 10 to the negative 4, and that's going to be negative 1. Okay, so far so good.
Yeah.
Okay, now let's just make sure that everything lines up. We're gonna be canceling out the H2s, so the H2s will cancel out, and that's gonna give us NH3 on the bottom. It's gonna give us I2 as well. We're gonna get 6 HI, and then we're gonna have N2, and then we're going to multiply the equilibrium constants, not add, like I said. And then you should get 1.1 times 10 to the negative, or 10 to the positive 9, my fault. Okay, something around there. Everybody good? I should probably line this up a little better too. Yes,
Like 1.63 times.
that's fine. Yeah, 10 to the negative 9 is the most important part. Yeah, 1 point whatever. Okay.
I remember that.
Hmm?
I thought the first one was the 1.8.
Yeah, my fault. I lined it up. I lined it up a little bit wrong or weird.
Yeah.
Um,
I thought
Yeah.
we didn't have to like second place. Like find it.
Yeah, sorry about that. That was a no, that was like a or format thing. My fault. Okay, I think we have time to do the next section. It's a little bit short, it's a little bit shorter than the previous one, so let's get into it. Okay, so sometimes you will have a heterogeneous mixture. Now, if you guys remember from way back in the day, we talked about homogeneous and heterogeneous. Homogeneous is where everything is the same state of matter, everything's aqueous, everything's gas, whatever. But in equilibrium, we're gonna have some mixtures that are not homogeneous. So you'll have different states of matter. So we got this example right here. We got a solid, which is going to produce 2 aqueous products. Now you guys are gonna love this. Okay, if you ever have a pure solid or a pure liquid, you can just ignore it. It doesn't matter. It doesn't have anything to do with your equilibrium constant. Okay, so if we write the equilibrium constant for this equation right here, ignore the solid. So we literally only need to do the product side. Easy peasy.
Only gases.
Yeah, only gases and aqueous. That's it. Okay, so I want you guys to write the equilibrium constant for this reaction right here. Okay, shouldn't take you very long. Okay, again, you're gonna ignore pure solids and pure liquids. This is if you want to jot down something, this would be what you. Okay, so take about a minute, write the equilibrium constant expression for this reaction right here. Okay, and be careful, it says in terms of partial pressure. Yes. Yeah, 1 over. Exactly. Good question. Okay, guys. So hopefully not too long to do this one. We're gonna ignore liquid water. So the Kp value, because asking for partial pressure, will be the partial pressure of H2O gas. That's it. And then, like Josie said, if we're gonna look at the reverse reaction, I didn't ask you to do this. It's just going to be 1 divided by the partial pressure of H2O. Okay, so this guy basically just becomes 1. Okay. Pretty simple, right? It's a lot easier than trying to calculate other stuff. No, it's not gonna get harder. What makes you think it's gonna get harder? What have I done in the past to traumatize you? Who hurt you? Who hurt you guys? Oh, my fault. Okay. All right, so let's do one of these together, and then we'll move on to the next one. And that'll be for sure the last question that we do. Okay?
For sure.
For sure. For today. No, for sure. Okay. Okay. On this paper towel, I will promise you. Yeah, that's how much my promise means. Yes, I do. I care so much. Okay, so let's do this one. So if we take a look at this equation right here, which one's the one that we're gonna ignore? Yeah, we're gonna ignore liquid water because it's a pure compound, pure substance. So we're gonna write the Kc, and so now we're looking at concentration. And so we're gonna put the concentration of CO on the top. We're gonna divide that by CO2 on the bottom and H2 on the bottom. So the point I'm trying to make is it's the exact same thing we've been doing. we just ignore the pure solids and the pure liquids, okay? Okie dokes, guys. You guys ready to try the next problem?
Wait,
And it does get a little harder from here, of course. I respect and love you all too much to keep it easy. Okay, so let's do 12.13. Now, 12.13, I ripped. No? No, I said let's do this one and then we'll do one more. Not 12.14. Wait, did I counter up? 12.13.
Was the last.
No. I said this one and then let's do one more. Okay, well, I threw the paper towel away, so it doesn't mean anything. You guys should know by now that I will lie to you. I will get your hopes up just to bring it down for my amusement. Anyway, okay, let's take a look at 12.13. Now, 12.13, I ripped out of the AP test. It's an FRQ problem. I know, I love ripping it off. I don't want to do my own work. Okay, why do work when somebody already did it for you? Okay, so these mixtures right here are allowed to stand in a closed container. Okay, so these are all separate systems. Now, this is the reaction down here, and I want you guys to basically tell me, will these mixtures attain equilibrium? Okay, so I might be like, what is he talking about? Okay, so let's do part A together, and then I'll have you guys try the rest of them on your own. Okay. Okay, so basically you put a piece of CaCO3 inside of a closed container. Okay. And then it's basically asking, is it gonna go to equilibrium? So anyone want to take a shot at part A? Do you think yes or no? Is it gonna go to equilibrium?
Yes.
Okay, those are the options.
Yes.
Okay, so the answer is yes. Okay, and the reason why is because if you put a reactant in there, it's going to decompose, right? Okay, so CaCO3 will decompose into CaO and CO2. Okay, until equilibrium is reached. Okay, so this solid right here will turn into this and this until they are in equilibrium with one. That's the easiest one. That's why I wanted to do it.
Wow.
Because I respect you a lot and I think you can do B, C, and D. Okay, so I will give you guys 2 minutes to try. Actually, I'll give you 1 minute to try B. Okay, we'll go over B and then we'll go over the rest of them together. So I'll only have you guys do one of them on your own. So I want you guys to try B. Take a minute and try that out. Okay, so for B, okay, the answer is going to be no, it's not. Yes, it is yes. Okay, the reason why is because if we put both products in there, what's gonna happen? Yeah, both products can react to form CaCO. Maybe products is the wrong word. Both compounds, because if it's a reverse reaction, the reverse reaction until equilibrium is reached. Okay. Okay, let's move on to the next one. Okay, we're gonna go to C. Okay, now C is the one that's a little bit tricky, and that's why I wanted to go over this one together. Okay, basically what it's telling you is that you're gonna put your reactant in there, and you're just gonna put one of the products. Okay, now the key thing that we need to keep in mind here is that the pressure is greater than the value of Kp. So the pressure is greater than Kp. Okay, so far so good on that one. Okay, so if the pressure is greater than Kp, okay, what that means is, does it want to increase pressure? Okay, so if the pressure is greater than Kp, which is the equilibrium pressure, the pressure it wants to be, okay, what does the system want to do? Does it want to reduce the pressure or increase the pressure? Yeah, it's gonna want to reduce, okay? The system wants to decrease in pressure. Okay? Now, if the system wants to decrease in pressure, okay, there's only one gas in there. Okay, what's it gonna want to do with the gas? Does it want to make more of it or get rid of it? Yeah, it wants to get rid of CO2. Okay, it wants get rid of CO2. Okay, so basically CO2 is gonna want to turn into CaCO3. Okay, but there's a problem here. What does CO2 need in order to turn back into the reactant? It needs CaO. Do we have CaO in there? No. Okay, so it wants to turn into this compound, but it doesn't have the other reactant in order to do that reaction. The only way that can happen is if CaCO3 produces CaO and CO2. But like we said, it wants to decrease the pressure. Is CaCO3 going to want to produce more CO2? No. And so since it cannot form more CO2, it also can't form more CaO. So the system is kind of in this stuck place where it wants to decrease the pressure, but it has no way of decreasing it. And so basically nothing is really going to happen in, oh, what is that? Nothing is going to happen in this system, okay? So the answer will be no, okay? And the reason why it's going to be no, if we want to say it very concisely, it's because the system wants to decrease in pressure to reach Kp. However, there is no CaO, and CaCO3 will not produce CaO because that will result in more CO2, which will increase pressure. Okay, something like that. I'm sure you guys can write it a lot better than I can. It's kind of a run-on sentence, but I'm not. I'm making this up as I go along. Yeah. Teaching you guys Elvish in here. This isn't real. This is Elven magic. You can, but not from me.
I mean, if you wanted to, could you make?
I could teach you some organic chemistry, yeah.
Okay. So could you make that you wanted to?
I know organic chemistry very well. I got an A.
You can't say it obviously out loud.
Yeah, I'm good at organic chemistry.
It's organic.
No. Yeah, you can take organic chemistry in college.
You should make an 8 chemistry class just for
I
us.
just want to do when we make atoms. The final